just say a few words about you and put it in a general context, and I think he has some lessons in cookery, I believe. Is that right? These are frying pans you got? They look like frying pans. Yeah, okay. So, first of all, I'd like to congratulate Simone for his distinguished career in Cyprus. He's one of these very few young people that adopted Cyprus as their country to be trained. I believe you've been trained at the University of Cyprus, and now he's with us. So, and he has received a very distinguished recognition as a young investigator. You graduated in 2019, I believe, your PhD, so it's only 6 years. And you're following a very steeply ascending, in the good sense, career in your scientific field. Now, the Cyprus Institute is a home to about 40 people who are non-Cypriots. So 40,000, 40%, not 1,000. Yeah, late night. 40% of our staff is non-Cypriots or non-Cypriots, and we have 27 nationalities working in the Institute. So we are a very international organization, and that's really the strength of it. So people choose this organization to be trained, to develop their careers, go to faculty level. This is good. 70% of researchers, young researchers in Germany are non-Germans. So if for a country to really stand a good chance of being strong in the international scene, must have this extrovert approach and attract people and, of course, retain them. Now, I was listening to a statement by the government recently that they are going to announce something about bringing the brains back to Cyprus. We like to keep some of the brains we have in Cyprus and keep them in Cyprus and give them prospect to develop. So I hope this brain gain that we have, because Simone is a brain gain for Cyprus, we give them opportunities to stay in this country and prosper. And yes, I'm very curious to hear what they have to say, what the government is planning about bringing more people back to Cyprus. And I finish off by saying that we are growing very fast in Cyprus. It is very true, the research ecosystem. And in fact, I saw some figures the other day in preparation of my visit to the United States that we now have 2 universities out of 12 in the top 500. Greece has only 1. So only in the last 35 years, this country is doing something in the right direction. At least in science, we are in the right direction. Okay, and the quality of research that's done, it's of international, very high international standards. So, Simone, thank you for choosing the Cyprus Institute to continue your career for the time being, and we're here to support you and others to prosper. Thank you.
So thank you very much, Stavro. Welcome, everybody. My name is Konstantin Dovroulis. I'm the director of Castor-C. I want to thank you for being here. We're here to celebrate today, celebrate Simone's success. As you know, he was chosen by the Research and Innovation Foundation to receive the award for young researcher in the physical and engineering sciences. And together with celebration, we will hopefully also get to learn something about physics, the state of the art in physics. I want to take this opportunity just to say a couple of words about Castor-C and, of course, about computational science, because Castor-C is the research center here that focuses on computational science. So if you read about the history of computing, and I strongly suggest you do it. It's a fascinating history. There are also some very good movies about it. And I can give you references to books if you are interested. The history of computing essentially started in the mid-40s, early 50s, with computers like ENIAC and EDVAC and then MANIAC and so on. And from those very early days, the very first thing that was running on those computers was scientific applications. The very first computer was used, of course, to do calculations for the thermonuclear bomb. But then very quickly people, realized that in order to solve scientific problems, we need computers, and we need the fastest computers. And in order to use these computers, we need algorithms. And so there was a virtuous cycle created between computer science, the science of creating algorithms, creating computers, and computational science, which is using these computers to actually solve scientific problems. Well, of course, later, many other applications were developed, like business applications and games and many other things. But computational science and computer science were, from the very first days of computing, basically, let's call them, twin sisters, or they were very much together, creating this feedback loop between them. So Castor C is all about this virtuous cycle. We hope to become a place where computer scientists like myself will be working very close with domain scientists from physics, biology, many other fields. And we hope that it will be an environment where this virtuous cycle is being, performed and expanded on a daily basis. So Simone has been exactly that kind of researcher, even though he is a physicist by training. He has been using computation very heavily in his research. More recently, actually, he has also been using machine learning. And so he is, I think, an excellent example of that kind of profile, that kind of researcher. As Stavros mentioned, Simone graduated in 2019 with a PhD in physics from the University of Cyprus and applied math from the University of Wuppertal in Germany. And he has been with us since then. He's now an associate research scientist, and he will tell us about his fascinating research now. So thank you very much, Simone.
Okay. Thank you all. Thank you, Stavros, for your introduction, and thank you, Konstantin. It has been so far a great pleasure to be here, and the institute has offered a lot of opportunities. So, exactly as Konstantin was saying, the topic I'm going to present today is something that is leveraging this interplay between three fields: high-performance computing, theoretical physics, and applied mathematics. But first, I would like to make a generic introduction to the topic, and this is why in this talk I'm going to take the long way and present to you something about the long search for new physics that we are trying to carry out with our work. So, in the first part of the talk, I would like to reply to three fundamental questions. Why are we searching for new physics? What are the big open questions in fundamental physics? And how do we search for new physics? This will be the first part, and then afterwards I would like to introduce some of the work we are doing here at the Cyprus Institute with our group that is composed by 2 professors, 3 PhD and 3 postdocs and many PhD students. So let's start now the journey in this modern physics with some historical facts. Let's take some steps back. Let's go back to towards the end of the 19th century, at the end of the 1800s. And this is a very interesting case, which is very similar to the situation we are finding ourselves nowadays. And it was a period where it was thought that physics was a nearly complete field. So at that moment, physics was, theoretical physics was made of 3 main theories. One is classical mechanics, where we have Newton's laws and Newton's gravity, and this is used, as you know, to describe how objects move, how objects orbitate, and and the gravity that all affects us here on the Earth. Then we had electromagnetism. This was something very new, developed towards 1850 and forward by Maxwell, who unified two theories, the electricity and magnetism, in one unique theory. And this unification was extremely powerful because it allowed us then to develop new technologies like the radio transmissions by Marconi. It was just starting there towards the end of 1895. And finally, another fundamental theory was thermodynamics that described how one can convert temperature and pressure into work, and this is something you also well know about, and it has fostered all the industrial revolution a century back. So with these three theories in place, many physicists have thought, yeah, like Lord Kelvin, there is nothing new to be discovered in physics now, and all that remains is more and more precise measurements. So this Kelvin is the famous one, the one of the absolute temperature, and this was kind of the common conception at that period. So let's have a look a bit on what still was left to solve. There were these small puzzles that were left to solve, but they weren't considered very important. One of these puzzles was, for instance, the black body radiation. So this is something quite interesting. It's a very simple experimental setup. We have a so-called black body, which is a rounded metallic sphere empty inside, that conserves all the energy that is put through. So by heating it, this produces energy, and with this energy is converted into radiation that is contained inside this sphere. So this radiation, represented by electromagnetic waves, was expected basically to be distributed between stationary waves within this sphere, and the expectation was that since as we decrease the wavelength, more and more waves could appear, the density of these states will grow exponentially as the wavelength goes to zero. So this was the prediction, the classical electromagnetic prediction, while the observed result, by observing the radiation that was inside, is actually this spectrum that has a peak, a maximum here, which depends on the temperature of the system, and then goes down to zero towards minimal wavelength. And it was something that was not explained by the moment by the current theories. The explanation to this came with Max Planck, that thought that actually energy comes in packets. This was the beginning of quantum mechanics. Comes in packets that are multiple of a specific energy, and therefore it would relate the energy of the electromagnetic radiation to its frequency, meaning that if we take this frequency very high, so that the wavelength becomes tiny, then the energy of the system will grow exponentially, and therefore this wouldn't be allowed, and therefore this would limit the number of high energy wavelengths. And by introducing this assumption, it could perfectly describe the observed spectrum, and this was the beginning then of all the quantum mechanics evolution. A similar example of an unexplained problem was instead the anomalous periodion of the precession of Mercury, where Mercury, the planet orbiting the Sun, it has a precession of each perihelion. So the position of this point moves in time. The prediction by classical mechanics was this one, where the observed number of this movement was higher, so there was a mismatch. Again, this was another of these small examples that was not wouldn't be explained by classical theories, but required, for instance, general relativity to explain it, and the general relativity correction to classical mechanics makes a prediction that is equal to the observed. So we understand now that the theories that were in place at that moment were not wrong, are still very valid theories, they work in our everyday life, but often the region where this theory fail are under extreme conditions, like are through very small effects, like the one of planets orbiting the Sun, or tiny particles. And though the introduction of these new approaches was revolutionary, because in modern physics and modern time allow us to make all these new technologies like lasers, quantum computing nowadays, or generativity allow us to use GPS and explains all the astrophysical process. So this was fundamental in that period, and nowadays, after a very exciting discoveries in the 19th century, we are in a similar situation where since 50 years, there are no major changes in physics. So we have these theories now. We have basically the standard model of particle physics that describes how nature works. But this model is extremely successful. It's working very well. And since 50 years, we do not have a new theory that could make a prediction that could be validated by experiments and does outstand the standard model. So nowadays, we are much more humble. We do not want to say that physics is at the end of it. There are still undiscovered mysteries. And therefore, this is our motivation to search for new physics. Let's see a bit what is our current understanding of physics. So let's now talk about how matter is made. We all know we are made of atoms. Atoms are those that compose our body. And but if we look inside the atoms, these atoms are then made by a nucleon and the electron that orbitates around it, and then the nucleon is made by other particles, protons and neutrons, and inside these protons and neutrons are made by quarks. So this is how, this is current understanding of the fundamental constituents of matter, and the standard model is now a combination of three theories: the strong nuclear force, the weak nuclear force, and the electromagnetic force, that combined together with proper parameters can explain the universe, can explain the small matter up to the how neutron stars are made. So all of these are existing objects that we have no experimental evidence how they're made, and the standard model can predict the phenomena within it. So, what I will tell you, this is a big topic. What I will tell you more about later in my talk is our work, which is the study of the strong nuclear force, that describes how the interaction between quarks and gluons made protons and neutrons. But this is a very interesting topic because it requires numerical approaches. But before going there, let's see now what are how the standard model has been extremely successful in the past 50 years, and how experiments and theory have matched and failed to find something new. So let's see now one of the very first big success of these theories, another experiment, which is named the anomalous magnetic moment of the electron. And this experiment is basically measuring how the spin of the electron, of this particle that is a magnetic moment and a spin, is changing as this is rotating within an accelerator. So the classical prediction is that this spin would remain aligned to with the precession of it inside the accelerator. But what we find actually is that the spin does not remain aligned and actually is turning around. Okay? So this is the experimental evidence, and this can be explained by QED by considering higher order interactions, and for instance by matching the classical prediction with higher order interactions, where you can imagine it like playing a pool game where a ball hits another one, and if we add additional balls, additional interactions, then this changes the phenomena. And so by introducing a next order interaction of the electron with photons, we find a correction that matches the experimental one and was one of the first big success of QED. This was done in 1948. For 20 years more, experiments have pushed the precision of this measurement down to the 13th digit. Here are 13 significant digits of this value. And theory has matched this effort by predicting the same interaction up to fifth order, 5 loops, which are basically all these kind of diagrams that are considering many other interactions. And you can see how beautifully the theoretical prediction and the experimental value are in agreement. Okay? This is something, this is actually the most accurate verified prediction of physics that is up to 13 significant digits. And this is something, a very huge success of this theory. Okay? So this is the level where this theory is successful. It's extremely successful, and people have hardly tested it. But still, this is an example. There are others. There are others, and if we, for instance, change the particle, now we're not electron, but we consider a muon, which is still electron, but 200 times heavier. This kind of interaction become much more complex because it's like going from playing a pool game to playing bowling. You know that when you play bowling, it's very difficult to predict what is going to happen to the pins. And the same way here, we do not have only QED interactions, but due to the larger mass, we have much more phenomena that are spanning the whole standard model. So they do not span only the electromagnetic one, but also electroweak and strong one. And Theory-DO has computed this. And for instance, this was one case where in 2020 was kind of a breakthrough, where the theory would predict a value that is 4 standard deviation away from the experimental one. This was a breakthrough very important for us because we are looking for evidence like this where we can try to search for new physics. And this was something that then a lot of people put their attention on. There have been new developments. And for instance, it came out that at the end, this tension that was observed was actually not that strong if we recompute this kind of contribution by first principle using actual lattice QCD, which is what I will tell you about. And by these new measurements, this tension is reduced, and nowadays this is not really considered anymore a strong signal on new physics. But why are we looking really strongly for new physics? Because we have unanswered questions. And so these are our laws that we use to say we need something more than just the standard model because these are things that the standard model does not describe. So 4 of the fundamental questions that we are trying to reply are, first of all, what is dark matter and dark energy? This is something, quite a difficult concept that I will not go very deeply into it, but basically by astrophysical observations, one would expect that the rotation velocity of galaxy, for instance, to decrease as we go farther from the center of the galaxy itself. But actually what one observes is that this, instead of decreasing, is plateauing. And this is again a similar example with the black body radiation where one expects something, but experiments show something else. The something else can be explained by the fact that there is actually more matter inside the galaxy than the one it's actually seen. And this is what we call dark matter, which is something that we don't see, but we theorize it's there because it's the only explanation to say this it should behave like that, right? So this is one, for instance, one of the reasons, but there are many others, why we are introducing the concept of dark matter and dark energy, which actually make 95% of the energy in the universe, while what we are usually used to, the ordinary matter, which is what we are used to every day, it's restricted to 5%. And these are large contributions that are currently unexplained, so these are the reason why they're dark. Another big question we are trying to answer is what happened to the antimatter? So this is another important concept of modern physics. We know that matter and antimatter can be, so that energy can be converted to matter. So this happens by the creation of pairs of matter and antimatter, for instance. So a photon can become an electron and a positron. And this is how it's theorized that the universe was originated. So there was a bubble of energy within the universe, and at some point this is splitted in the creation of matter and antimatter. But for some reason that is still unknown, only matter has survived, and the antimatter kind of disappeared. So for the antimatter to disappear, there requires some symmetry breaking that at the moment are not explained by the standard model, or actually partially explained because the standard model can predict some of this symmetry breaking, but they are not strong enough to predict the currently observed equilibrium between matter and antimatter. And this is why, this is another important question, is how the universe has originated. So the Big Bang is the currently established theory, but still cannot explain why we only have matter. Another very important one is how can we unify gravity with quantum mechanics. We have 4 fundamental forces in nature. 3 of them are unified in one unique theory, the standard model. One strong force, weak force, and the electromagnetic force. And the big question is how to put together gravity with that. And this is a very big challenge because the scale of these forces are very different, and the gravity is one of the weakest one that has only effect in this very large scale with very large masses, and it has very few quantum effects. So this is one of the reasons why this is very difficult to discover, to unify. And finally, the other big question is if there is something more than what we know. So are there other things that are unknown? Is this the end of it? Can we go deeper inside quarks? Are there, for instance, the existence of string theory and supersymmetry? So, like I said, there have been developed many more theories in the past 50 years, but the big problem is that none of these theories could make predictions that could actually be confirmed by experiment and validated. So this is the reason why we're searching for new physics. How do we do it? Well, on one side, we do it experimentally. So there are very big experiments. There are experiments that you might be familiar with, like accelerators at CERN, that this is called the energy frontiers, where we accelerate very high energy particles, make them collide and looking for what comes out. There are others like astrophysical, cosmological ones, through telescopes or gravitational wave detectors, as well as intensity frontier, where one has very big detector running them for a very long time and hoping to see something unexplained. So these are three kind of experimental setups, which are matched by theoretical setups used to also make theoretical predictions and try to validate validate the theory with experiments. And here we have, for instance, the phonological setup, which is, well, let's start from the theory. We have the theory, which is pure theory, is what we know. But theory alone nowadays is not enough anymore. And for instance, this is matched either with experiments giving rise to phonology, which is trying to model the experimental data, as well as theories matched with simulations using computers and trying to make predictions. And this is, for instance, the field I'm going to tell you about, which is lattice QCD, which lays here in the between theory and simulations. Okay, if there are any questions, please ask. Otherwise, now I will move to the second part of the talk, which is about what we do. Okay, so there is, of course, time for questions at the end. So what is our work about? Like I said at the beginning, our work is something that is very interdisciplinary. It lays in the between of these three fields: theoretical physics, high-performance computing, and applied mathematics. Let's start with, now the talk will become a bit more technical. I will try to, hopefully it wasn't yet much, but I will try to keep it at a higher level. And let's try to understand what we are actually studying. So what we are studying, as I said, we want to study the content, the fundamental constituent of matter. So we want really to understand how matter is done at the tiniest level by studying the content of protons and neutrons. And these protons and neutrons made of quarks kept together by the strong nuclear force are described by the theory of quantum chromodynamics. A very interesting aspect of this theory is the chromo part of it, which, by Greek means color. So this theory predicts that this kind of matter brings together a color index. This color degree of freedom, it's very similar to the charge degree of freedom, where you have things that are positive or negatively charged, and since they're positive or negatively charged, they might attract each other, etc. This is what does electromagnetism. At the same way, here things have not positive or negative charge, but they have actually three colors. And the colors conceptually not because they're colorful, but it's something that really helps us to understand how these forces work. And this force works to such that combinations of this matter with different color are put together always to make an object that is neutral color. So if we put together something red, green, and blue, you make the white color, and this is neutral. Okay? In the same way, if you put together red and cyan, which is considered anti-red, you make something neutral, which is, again, white. So you can put together matter of different colors, right? And you cannot separate it. So the matter at this level is always combined such that a neutral color is the result of this combination. Okay? And this is why we cannot separate quarks from each other, because if we try to do so, for instance, a big property of it is confinement. If we try to separate two quarks, the force between them will act like a spring. This is one of the reasons the gluon, that is the force carrier, is always represented as a spring. If we try to separate them, the force between them will act as a string, will act as a spring, and so we need to put more and more force to separate them, but at the moment we put enough force to create a new particle, well, then a new particle is created such that still the neutral color appears. So a particle with color and anticolor is created and makes again two hadrons. So in the same way we can break up a spring because we put much force, here also we can break up hadrons, but not by having two quarks in our ends, but having two hadrons again. So it's very impossible to have, at the end of the day, something that is just quarks. You can have it, yes, if you go at very high energy and you go in this regime known as quark-gluon plasma, but this is not the regime we are in. Another very, very important feature of this theory is the fact that is the reason why we have mass. Indeed, 99% of our mass, it all comes out from the QCD interaction. I think many of you are familiar with the concept that mass and energy are related. And if we look, for instance, how the mass of the hydrogen is separated, now apologies here for the units, but these are units that we use in expense. So MeV means mega electron volt, and this is the typical energy how it's measured. And you can see that, for instance, an hydrogen atom has 0.5 MeV coming from the electron, 940 coming from the proton, and only 13 EV, which is missing the M, so it's 1 million times smaller contribution coming from the energy binding. On the other end, if we look at this mass of the proton, that is 940, we have the opposite situation where the mass of the up and down quark, which are coming from their mass of the constituents of these quarks, it's only contributing 1%, while 930 MeV is coming from the energy binding. So all the mass of our protons is actually coming from the energy, the interaction that they do, and not from the mass itself of the constituent itself. Okay? So this is why understanding this energy is very, very important. It's very important, but it's also very difficult because this kind of interaction we have here are extremely complicated, and you cannot just solve them using standard tool like perturbation theory that we saw before for QED, where we had all these various interactions, because actually it's like a series that is not converging. It's a series that requires all orders to be considered, and this is why we need numerical simulations to solve it. And the way to solve it via numerical simulation is by basically taking the continuum theory. We then discretize it on a lattice. So this is the only way we have actually to simulate something. To simulate, this is something very common in physics because it's impossible to simulate a continuum of values. You need to always discretize it. This is done everywhere in finite elements, in lattice Boltzmann, etc. You need to discretize your theory. You put it on this lattice that are finite amount of points. And once you discretize the theory, then you can compute observables that depends on three parameters: on the lattice spacing, the distance between 2 points, on the size of the system you are simulating, and on the parameters of the theory. A very important step now, then these you can measure them. A very important step to get the physical final quantities to take these, all these artifacts that you are doing by simulating it on a computer to their continuum value. So you want to take the volume to infinite, you want to grow it up. You want to take the lattice spacing to 0, you want to make it finer, like you approach a continuum, and you want to match the physical parameters of the theory, like the mass of the quarks. Once you do that, you control your systematic effects, you obtain predictions that are very well matching the experimental results, like here. And this was the year 2000 was one of the moments when this theory really started revolutionizing and giving prediction that could match experiments. Indeed, the theory went through a very, very long evolution, starting from 1980s when it was formulated up to nowadays. And during these evolutions, the theory became much, much more complex. So we simulated bigger and bigger volumes. This is one of the reasons why we need the largest supercomputers in the world to actually solve these problems. If you consider the number of degrees of freedom here in one of the largest volumes we simulate today is are 288 gigabytes of one single configuration. So, 288 gigabytes, it's something your laptop is usually a few gigabytes. One single configuration is this size, and we don't use one, we use 1,000 of them, times more. And you understand that indeed the amount of data we use, it's order of billions of this amount of gigabytes. So this is why we need larger supercomputers. It's very computation intensive. And it's one of the reasons actually we are very successful in using these larger supercomputers. And this, for instance, this plot is something that we did it's a study we did very recently where we are scaling our application. And you can see that we can reach up to 500 nodes of a GPU system with 4 GPUs per node, so around 2,000 GPUs. We can use an order of 2,000 GPUs. And by demonstrating this, we could get the certificate that our application is exascale ready. This was a condition to be able to use the largest supercomputers in Europe that is going to come up, which is Jupyter, and is the first exascale system. So the fact that our application is so computationally demanding also allows us to use some of the most advanced technologies that we have in HPC in Europe and worldwide. And this is indeed to give you an idea here. This is the curve of the cost we have used over the years for simulating larger and larger systems compared to the size of the largest supercomputer in the world, which is, for instance, currently Frontier. So this is why our theory is computationally demanding, but this is solved by supercomputers. Another important aspect of this theory is being able to simulate it, and this requires very advanced algorithms. And for instance, this is just to remark here, I don't want to go into the details, but I want to show you here how by changing the algorithm we use, so going from a standard solver to a multi-grid solver, we could actually accelerate our calculation by a factor of 30. So we could simulate 30 times faster we produce 30 times faster our results, and this would really allowed us to do some important work and anticipate of many years the advancement that would be needed by HPC. So by changing the algorithm, we could then simulate many ensembles up to a lattice size that is our state-of-the-art nowadays, which is this order of billions of degrees of freedom and gigabytes of data. Okay? And finally, the last step we have to do is to take this continuum limit, which means simulating many of these ensembles at different masses to different volumes, extrapolating, and this is our final result. And you can understand also here how important it is to advance these algorithms such that we can get closer and closer to the continuum limit, make our lattice spacing finer and finer, such that our final prediction is more accurate than what we can provide right now. Okay, don't worry, I'm at the end of my talk. So basically, what do we do with this? With this technology that we developed, we have then a very rich spectrum of physical quantities we can analyze, produce, and contribute in the discovery of new physics. So 3 examples are here. For instance, we can provide the input to experiments. And this is very important because if you assume the standard model to be the theory that describes nature, then you can actually use it to complement experiments in regions where, for instance, they do not have very high accuracy. Take as an example here of the weak decay of a neutron to a proton. This is needed for the study of neutrinos. Having more information of the values of this cross-section here, it's very important. And this is something we can accurately measure, and this is our result that contributes to this study, and then used by experiments to improve their precision. In the same way, we are searching for new physics, and to do so, we need to do precision physics by making very accurate theoretical predictions that can be compared with experiments, searching for discrepancies. And in general, our work aims to increase our understanding of how our constituent matters, how we are done, like the structure of protons and neutrons, and this is why we put also a lot of effort in understanding better how the various contributions between quarks and gluons are giving us the mass, the spin, and a lot of other properties of the resulting particle. So this, of course, uses the largest supercomputers in the world, and these are the computers we are using, like the current largest in Europe, and then we have been habilitated to use the first exascale systems, then we have ALPS the second, Leonardo third, etc. And of course, it involves a significant collaboration effort. It's not just us here in Cyprus, but it's a big European and US effort that we are contributing in to produce these results. Concluding, what I showed you, it's, I wanted to try to give you a grasp of what we do in our research, which is known as lattice QCD. This is cutting-edge research in particle physics. It's quite advanced, and it's an honor that the Institute is funding this research for, and where it's a field that we are actually quite competitive worldwide with our group. And it's a very field suitable, like Konstantin was saying, for Castor C, because it's a highly interdisciplinary. Besides having a strong basis of theoretical physics that motivates our research, then strongly relies on high-performance computing and applied mathematics to develop new algorithms and to perform these calculations. Looking forward, actually, it's even more interesting because the introduction of new technologies like machine learning and quantum computing, it's really expanding our horizons because these new technologies would allow us in the future, most probably, to solve some of the open issues that we have in our calculations, like going very close to the continuum limit through machine learning techniques, as well, this is done via normalizing flows, as well as developing noise reduction techniques, also using machine learning. Or on the other hand, quantum computers are also the next technology that is going to replace high-performance computing in our field, most probably, because they really act as quantum simulators, so you can really simulate quantum mechanics in these systems, and basically they provide a solution to the same problem, allowing us then to explore new frontiers in this very complex phase diagram of QCD, which at the moment is just restricted to this area where we have a zero baryon density and from 0 to very high temperature. And this is the moment we can actually grasp of these complex physics systems, but would be very, very interested to go further and study, for instance, more in details how neutron stars are made and actually how nuclei are put together by studying multi-hadron systems. So we believe that our future is bright, and we have a lot of opportunity to exploit more technologies in the future. And yes, this is what we do. Thank you all for your attention. I'd like to thank collaborators, Dina, Yannis, and Jakob, especially for their work and collaboration these years. Thank you all. Okay. I guess if there are questions with the microphone, it's, yeah, there is a question.
Thank you for beautiful presentation and talk about how to use high-performance computing in quantum electrodynamics and chromodynamics. And I'd like to know if you know some top IT companies such as Microsoft, Google, or I forgot some department of Elon Musk companies that developed artificial intelligence, they have some troubles that all this high performance facility requires a lot of energy. Also, I'm from Ukraine, and I know that lack of energy is a big problem when some power plant is destroyed. So is it planned in Cyprus to build some new power plant for building high-performance computing, because high-performance computing requires a lot of energy to calculate?
Okay, let me reply. Yes, so we avoid the noise. Thank you for your question. So yes, maybe I will exploit this to reply. Let's say your question is mainly about Cyprus, if Cyprus is going to develop supercomputers that are competitive with those worldwide. I think I don't think this is a plan, but what Cyprus does is to join this European effort that is named UNHPC. I don't know if you know about it, which is an European joint undertaking involving many countries in Europe, and is actually the one funding all these supercomputers. So most supercomputers are funded through European resources that also Cyprus is contributing. So these are the current setup of UNHPC is co-funding, where the countries and the European unions put 50-50 of the monies. Then these countries join in consortia, okay, big consortia, where, for instance, take Leonardo in Italy is not only funded by Italy, but is funded by many other countries, okay, that are putting money to fund the supercomputer, and then they have benefits from it by using it. Because to use this technology, you don't need them to have them in place. You just connect remotely. We use all of these, we connect remotely and just use them. So you need a center like Cineca in Italy that is going to host the computer. It requires the hardware, and then everybody can join. So, for instance, I think Cyprus has joined a consortium of Greece with Daedalus, with the new supercomputer is going to be up in Greece, and this is the kind of effort is funding. Then, of course, here locally we have our systems, but they're not nearly comparable to what we have here. So, take at the Institute, we have the Cyclone supercomputer, right, which is of hundreds of teraflop performance, so it's a factor of, let's say, few hundreds magnitudes smaller than, a factor of some hundreds smaller than these systems. And it's used to produce code. We mainly use it for analyzing data, and then develop codes that then we are going to deploy on these larger systems. So also with the National Competence Center here, we use it as a way to help people locally for then deploying the calculations on these largest European systems. Okay? Yeah. Konstantin.
Simona, thanks for the very nice talk. This last part that you mentioned, so after the simulations are done, right, you have this humongous amount of data and you analyze it. So what are you looking for in that data? I mean, what is the data mining exercise that you do, basically?
Okay. Well, yeah, it's, let's say the data mining exercise starts much earlier than the final data. It starts during the productions, because what we compute on these lattices are basically, well, I don't have something to complement this, but are basically quark propagators that represent how this matter interacts with the vacuum, etc. And then we go there and start measuring quantities, right? We measure observables. We measured as much observable as possible. We're still producing order of petabytes of data. But at runtime, we are trying to save as much as possible for then post-processing and extracting the quantities, okay? So what ideally would be great to be done is to replace these, and very often then it happens that we say, shit, if we had measured also these, we would be able to compute also that, but we didn't do it, and then this is lost, right? So it's this is an issue of doing it runtime, and then this requires running again with new stuff. So something that, for instance, we see machine learning to help a lot is for doing some runtime data processing and extraction information and compression. But one needs to be very careful because, of course, what we do, we want to be exact. It's never approximate. It's not like we cannot allow for any additional error on top of it, right? So this is a bit the critical difference between what data mining and what we do, because we are actually, yes, measuring directly the quantities we want to measure, right? So we have first a theoretical work that tells us what we need, the ingredients, we measure them, and then afterwards we put them together and get the result. Yeah, so it's...
so you know a priori what should be measured, all the observables?
I know a priori the ingredients I need for specific observables. But this is, of course, always motivated by observables. So something new, then they ask us from experience, and we would like to know also this. And either we are lucky and we have it in our data sets, in our storage, or we are not, and one is to start a new campaign. And this is a similar problem with experiments with the detector that store data, but the data produced by experiments is huge. You cannot you cannot really store everything. So the order of petabyte we store is already selected. It's not it's not all the data we produce at runtime. That's of the order of exaflops, of petabytes, right? So, yeah.
Yeah, I mean, I don't know if others have questions. Please. I have
Maybe.
Thank you very much. I have a layman question. Are there any lattice QCD predictions there at the forefront of computational chromodynamics that could hint towards the ultimate decline of the standard model? That the standard model is really incomplete and we have to go beyond.
That's the issue, right? That I don't think nowadays any physicist would say that this is going to happen, because like the same for classical, from Newton's gravity, nobody will ever tell, I mean, Newton's gravity studies in textbook, it's not something that it's wrong, right? In the same way, the standard model, it's not wrong. It has 50 years of success and it has really strongly tested. The only thing we are looking for are small extensions, so regimes, right, where the standard model does not apply anymore. And this is the same that was done with spatial relativity, general relativity. So in case of spatial relativity, also there, the movements of particles predicted by, objects predicted by classical mechanics works as far as you don't make them go very, very fast and approaching the speed of light. If you make them approach the speed of light, then it doesn't work anymore and you need spatial relativity, etc. The same thing here for the standard model. What we know is that it works. It works extremely well. What you might need, it's either a more fundamental theory, right? Let me go here. It's either a much more fundamental theory that can describe everything, and so you put it even lower, so you consider standard model as more effective description, right? And then you have even something smaller than quarks, etc. Or you need small extensions that for correcting for these small effects that are missing. But this is what we need. No, there are no evidence at the moment that this is the case. So the string theory does that. I don't know if you're familiar with string theory, but it tries to do that. It tries to describe something even more fundamental than the standard model.
And unexplained results that are out there basically can be matched.
Yeah, nothing hints to the existence. Nothing apart these very extreme conditions like universal and unification, etc. So, but at the moment there is nothing special.
I want to ask one more question, if I may, now that you asked the question that it's more like on the high of the side. So my question is, I mean, does it bother physicists that the standard model is, it's basically too many parameters, too many particles. It's not a parsimonious model, and I think we like to believe that the world works based on very parsimonious explanations, and the standard model is not like that. So,
well, okay, yeah, there are questions like that. The naturalness of the standard model is also a question, right? The big question, for instance, are why there are three families. There are three families of quarks, there are three families of leptons, so why there is not a fourth one, why only three? We understand now where the mass of this comes from. This comes from the Higgs boson, but like I said, this contributes to this small mass we have here, where they have it, yes. Yeah. The Higgs boson is not contributing to our mass. It contributes to these mass parameters, right? Then the energy binding is the one contributing to our mass. But still, the Higgs boson explains all these, the mass of the particles. What else? Of course, this a bit bothers may bother physicists, why we cannot go smaller also, if there's anything smaller. But it works, so it's... Now, this is why new theories have been developed, like string theory. It's very fascinating, and a lot of people spent a lot of time on string theory, but until they cannot make a prediction that can be validated by experiments, then that's just a theory. So it's a very beautiful theory, but just a theory. And this step is missing for these new theories, right? So people have explored these ways to unify everything, but you need to make a prediction to match nature. Would be a beautiful world with many, yeah, you can create many other beautiful worlds, but this is nature, so you want to, yeah, right.
Cool. Any other questions?
Okay.
All right.
Thank you all for coming. Thank you. Thank you, Cyprus.
Quantum chromodynamics, you have some particles, which is complexity of calculation of time evolution on number of particles.
Yeah, it's needed. So the problem what you said so far, it separates the ion